In this video, I would like to just look at the stadium wave function. It's an example that we're going to be using many times this semester, and all I want to do is use the basic technology we're going to use most of the semester. We will also be using Play-Doh now and then, but not today. But here's the problem. It says, suppose z equals h of xt equals 5 plus cosine 0.5x minus t represents how high in feet the head of the person is who is sitting x seats from the main aisle t seconds after the stadium wave begins. The idea is somehow, some way, this is a formula that we can use to sort of mimic what the wave is actually doing. Now, the most important tool we have for studying functions, you can see this in the big box, says study the one variable functions we get when we hold all but one variable constant. So for the most part, what we're going to do is just go over to Desmos, just see what happens when we hold one variable constant and what kinds of questions we can answer. We're going to go back and forth between doing this. I think today I will probably just use this in Desmos. I will frequently have a Google Jamboard open so I can just type out stuff so you can see it written and we can reference it later. I will also have a little whiteboard out so that we can at least do some calculations by hand without having to type everything out. Meanwhile, I'm going to go back and forth between this page and Desmos. I'm going to look at the first question. It says, what is the value and meaning of h of 3, 2 in this context? Well, what I'm going to do is go over to Desmos. I'm just going to go right in here. I'm going to type in h of xt equals 5 plus cosine of 0.5x minus t. You see, it graphed nothing, which is not always helpful. But at the moment, we just want to know what h of 3, 2 was. So I'm going to press enter, and I'm going to type in h of 3, 2. And I get a number. This is 5.8777 something. What I'd like to do is annotate this. So I'm just going to go to the plus sign and add a note. And I'm just going to say, this means that the person in seat 3's head. How about the head of the person in seat 3 is 5.878 feet high 2 seconds after the wave began. This already does illustrate one important thing, by the way, is that when we want to start using multivariable functions for real-life situations, the explanations start getting really long. Anyways, we've done the first thing. We evaluated a point, and we have an explanation, which is not bad. Let's go see what the next thing we're supposed to do. Because if we hold t constant at 2, we get a function of one variable that we know how to study. What does its graph look like? What does this function represent? Well, so I'm going to go back over here. I'm going to press enter. And we're supposed to hold t constant at 2. Well, what I'm going to do is just go to h like this and put in a 2 for t. And you see, bam, we get a picture out here. Now, what is this? Well, it's certainly a cosine of something, right? In real life, let's see here. If I add a note, just so we have it annotated, h of x2 equals 5 plus cosine 0.5x minus 2. In a trig class, if I wanted to graph that, I would pull out the 0.5 in the following way. I'd write cosine 0.5 and then something like x minus 4. That's right. Now, in a trig class, we know that the 0.5 actually takes the original period and doubles it. And the minus 4 moves the peak of the wave 4 units to the right. So in terms of what we would graph in a trig function, in a trig class or a Calc 1 class, we would start right here, right? And we would just go from here over to here. So what is this? Well, let's add a little note here too, just so we can do this. What is this? We froze t at 2. That makes this a snapshot of the wave when t equals 2. All the x's are frozen, so I'm happy with that. Now we can actually see what's going on here, right? For example, the highest any head gets here is 6 feet high. the lowest any head here gets 4 feet high. So I'm already going to criticize the wave a little bit. I think from sitting to standing, we should actually have a bigger amplitude, but that's all right. I don't like that this wave goes forever. No stadium wave goes forever. That's ridiculous. We've got being seated -5 seats away from the main aisle. That makes no sense. We might think left or right. I mean, that might be okay, but I don't like it. Plus, what I really don't like is if you remember what a stadium wave looks like, people get up, sit down, and then for the most part they're sitting, and then get up and sit down. This should look more like a heart monitor. But in terms of what I wanted to do, I do have people going up and down, which is good. I can take a picture of what's going on, which is good. And I think we've at least described what's going on without killing ourselves. Let's go back and see what the next question is. We already critiqued the model. Yay. It says we can actually calculate the speed of this wave. Just take 2 snapshots and see how far the peak of the wave moved in the amount of time between the 2 snapshots. Well, this is one thing that Desmos does that's better than some of the other things we want to use. I want to take another snapshot. Now, we took a snapshot when t equals 2. How about if we take a snapshot when t equals 0? So that should give us something like h of x 0. And you can see the blue one is the snapshot when t equals 2. The green graph is the snapshot when t equals, let's see, blue is at 0. Green is at 2. So it looks to me like the peak actually moved from here to here in 2 seconds. Now we can actually get Desmos to show that. What I'm going to do is I'm going to write down something like h of x a. It would be nice if it would treat t like a parameter or a variable. It just doesn't want to do it. So what I want a to be is I want a to start at 0, and I want it to go to 2. And I'm going to make it the step 0.01. Of course, it doesn't look like anything's changed. Let's see here. What color do I want? Let's make the color... Kind of color. It won't change the color for me. There we go. All right. I want the color of the moving one to be red. So here we go. Now you can see at the very beginning when a equals 0, the blue one and the red one are in the same spot. And you can see as I slide a to the right, you can see the stadium wave moving, right? So sure enough, the stadium wave from 0 to 2 actually moved 4 units from right here to right here. And let's add a little note that says that. Adding a little note that says that. We can see that the peak of the wave moves 4 seats as t goes from 0 to 2 seconds. So the speed of the wave would be 4 seats in 2 seconds, and that's just 2 seats per second. And we just got that really by taking 2 snapshots. We confirmed it by actually adding a slider and having it move. And I'm now going to make another criticism. A wave that only moves 2 seats per second is ridiculously slow. I mean, even old alumni move faster than that. But we did calculate the speed of the wave, which is great. Let's go back to the question. This says, okay, I think for the most part, we're done fixing t and letting x vary. What happens if we fix x and let t vary? So we're going to go back over to here. I'm going to shut some things off. And we're going to look at our original h of xt. What do I want to do? I want to fix x at 3 and let t vary. Now we're going to see that it's not going to like this. Right? If I go h of 3t, it won't do it. It won't let t function as a normal variable. It always wants it to be a slider variable, which is just driving me crazy. In fact, it's the only thing it'll let me actually be a variable there is x. So what I'm going to do is add a little note here. Let me add little spaces right here. I'm going to get rid of that slider because I'm not going to need it. Adding a note saying that darn Desmos will only let x be the variable. So what we need to do in order to make Desmos graph something, we need to rewrite it, R-E-W, so that it reads h of 3x. Now we really mean h of 3t, but I'm stuck. I want to use technology for something. If I now write h of 3x, I got the picture I wanted, which is great, right? Mind you, this is not a snapshot, right? Because x in this case is actually playing the role of time, and 3 is what we're focusing on. So in this case, we are absolutely 100% not looking at a snapshot. What we're looking at is the motion of the person's head in seat 3 over time. Yes, let's add a little note that says that. This tends to not be as useful as snapshots, but we can at least say, hey, this is what we got. What we're looking at here is, we can call time lapse, right? A time lapse photography of the person's head in seat 3 over time as it bobs up and down. I think that's already an awful lot that we've introduced, which is great, but we'll use this example many, many times. In the homework, what I'm going to do is give you a slightly different example to look at and try to analyze it the same way. And in the end, then I'm going to ask for something different. And let me just talk about for a second what I want to ask you for something different. Let's go back up to the original one right here. This is what happened when we froze TIA2. One thing we mentioned when we just got started, when we wrote it like this, we saw that the length of the wave, so the distance from peak to peak, is determined by this 0.5. Remember that 0.5 does not say the distance from peak to peak is 0.5. It says it's actually, since it's going up and down half as fast, the distance from peak to peak, instead of being 2 pi, is now 4 pi. And you have to remember that from trig as well in order to finish that next problem. And good luck on the next problem.